Is life rare? We live in a solar system and a time where we know of only one example of life occurring in our own star system, us, Earth. But we are also tantalized by a number of other worlds in the solar system that might once have had or may still have life, albeit in a microbial form. This list includes Venus, Europa, Mars, Titan, Enceladus, and others. But until we go to those places and see if there is indeed life, or we solve the mystery in the laboratory of just how easy it is for abiogenesis to occur, we won't know the answer to the question, but we can glean clues. My guest today has been working on a statistical analysis that could shed some light on that question. How rare is life? How rare is intelligent life?
You have fallen into Event Horizon with John Michael Godlier. Dr. Kipping is the Assistant Professor of Astronomy at Columbia University, where he researches extrasolar planets and moons. Dr. Kipping also leads the Cool Worlds Lab at Columbia, which includes a YouTube channel and a website where you can learn about their research. Dr. Kipping's other areas of research interests also include study and characterization of transiting exoplanets, exoplanet atmospheres, Bayesian inference, population statistics, and understanding stellar hosts. He is also the principal investigator of the hunt for the exomoons with Kepler HEK project.
David Kipping, welcome back to the program.
Hey, it's my pleasure to be back on. Thanks for having me.
Now, David, you have a new paper out, and this paper looks at a Bayesian analysis of the probabilities of life and intelligence. Can you give us an overview?
Yeah, sure. What I wanted to do was to sort of imagine if we reran the tape of history of Earth, how often would we expect life and intelligence to reemerge? Now, you might ask, why am I so focused on rerunning the tape? And the reason is because I can't really, if I'm being honest, I can't really ask questions about other planets. I wish I could. I wish I could tell you about Proxima Centauri b and Alpha Centauri planets, but the problem is we just don't have any data about those other planets, whether those conditions are similar to the Earth or not. So we just, in this paper, focus on the Earth, but if Earth-like planets are common, then by extension, you could apply this analysis elsewhere. And the data we use when we look at the Earth is just the timings, that's it, the chronology of evolution on the Earth. So when we look at the Earth, we find that life started very quickly within the first quintile, the first 20% of Earth's habitable window. And us, intelligent life, however you want to define it, actually doesn't really matter too much how you define it, doesn't really change the numbers too much, emerged in the last quintile, the last 20%. And so in the paper, we take those two numbers, we ask, what does that mean? Does the early emergence of life and the late emergence of intelligence tell us anything probabilistically? And the summary takeaway point, I suppose, is that I can give you betting odds, or really I'd say Bayesian odds, but betting odds is a bit more understandable perhaps, that I would say that life is common, life would reemerge, is 9 times more likely than life would not reemerge if you reran the tape. That's sort of the final takeaway message. And for intelligence, it's more difficult to say conclusively, but we find 3-2 odds against intelligence. So it's very subtle. I mean, 3-2 is not the sort of odds you'd bet your house on, or it's pretty close to 50-50 to be honest. But our late emergence does slightly nudge us towards a more pessimistic view.
Now, if you look at the history of Earth, there are a couple of very telling things, I think, that suggest that life or intelligence is rare. And one is the leap to eukaryotic life, which took, 1.8 billion years before life went from very simple to something more complex. Does that play into the equation? I mean, did you account for that weird long period of simplicity?
Yeah, it's weird you mention that, because that's almost how I started the paper. So this has obviously been a big project of mine for a while now. When I first started it, I was very much inspired by a paper by Brandon Carter, who, I think the title of the paper was 5 or 6 Steps to Evolution. And he was doing sort of also a statistical analysis of the chronology of major evolutionary transitions, and actually trying to figure out which of these transitions are probably critical to our success, our existence. And so some of the examples would be the emergence of eukaryote cells, combigenesis, sex, the swapping of genes. There's the adaptation of multicellularity. And so he comes up with 5 or 6 of these. Eventually, the last one is, of course, civilization. And makes an argument that if these transitions are all very, very difficult, then the spacing between them, let's say the typical transition time from eukaryotes to multicellular life is 10 billion years. That's the typical transition time. Then we're only here because it happened unusually quickly. In fact, all of the transitions are just like that. We may just be a product of a series of unlikely events that just all happen to happen quicker than usual elsewhere in the universe. And then if you looked back at the spacing of those events, even if the transitions are different timescales, as long as they're all long timescales, like many billions of years timescales, then they would appear evenly spread across the evolutionary record. And that's kind of what you see, in fact. So that was a real inspirational paper for me when I was working on this, but I couldn't really figure out how to do any better than what he'd already done. So instead I kind of switched gears, and I just asked, what's the probability of getting to that final point in the first place? And I kind of, by treating it that way, I can sort of fold all of those steps into just one. I mean, any of those transitions, if you think about it, is probably also a sequence of smaller steps that allows eukaryotes to happen, or allows combigenesis to happen. It's also a series of sub-steps that are probably necessary. And the same way here, I'm really treating all of those major transitions as just sort of part of one overall transition, which is from dumb life to smart life. And that's just treated as one parameter in the paper. And that just really simplifies the mathematics.
I suppose the obvious question is that, okay, you have that long period between the leap to eukaryotic life, but then you have another long period of the leap to intelligence. And there is no guarantee of human level intelligence. Just very specific evolutionary pressures created our intelligence, and otherwise you might just have a world of octopuses or dolphins or something like that are of lower intelligence but not able to create a civilization. So doesn't that factor in that you might have locked in life that's intelligent but just does not have the physiology to create a civilization?
Right. Yeah. A good sort of definition for thinking about this is that we really pose this in terms of the Drake equation. And when Frank Drake wrote that down, and I think even Seth Shostak has directly said this, that the FI term, the fraction of life that goes on to form intelligence, really what we mean by that are the intelligences which could build radio transmitters. Really, that's really what they're talking about in that equation. And then the next term, FC, is the fraction of those that go on to choose to do so. So if you define intelligence differently, and you say, no, I'm not going to define it as the fraction of life forms that can build radio transmitters. Instead, I'm going to define it as anything that has an IQ higher than 1.5 or something. So, maybe relax that a lot more, however you want to define it, a certain number of neuron counts or something like this. Well, then you would find that FC would drop dramatically. So you can define it however you want, but it would affect the next term in the Drake equation. The definition of FC would then change, because it wouldn't be the fraction of those who can build radio transmitters that do build radio transmitters. It would be the fraction of anything with an IQ greater than 1.5 that goes on to build a radio transmitter. And that would be a different term that you'd be putting into the equation, even though it would have the same symbol, perhaps, and that would be confusing. But it's just important that all of the terms in the Drake equation are conditional upon the last term before it. And so in that sense, you can define intelligence however you want, but I think when we think about the Drake equation, it's more useful just to focus on the things which really could communicate with us or could spread out across the galaxy.
Now, do you think that radio is the right place to look, or do you favor another technosignature of, whatever CFCs in an atmosphere or something like that, or the incomprehensible, something we don't know about? Do you think that we're a bit naive in looking in radio?
I think all of the above. I think my honest answer is we don't know. We don't know how other civilizations would choose to communicate with us, or even not choose to communicate with us, but serendipitously reveal themselves, accidentally reveal themselves through the product of their technology. So this is why a multi-pronged attack is really the best we can do. I mean, if anybody tells you radio is the only way we're ever going to detect civilizations out there, I'd be very skeptical, and you should be too, because maybe radio, we're already seeing a transition away from radio technology ourselves as we move towards sending our data through fiber optics, for instance, that really doesn't have any leakage. So it's not obvious that we can put all of our money on any single one of these bets. And you could say, well, let's look for lasers then, or let's look for gravitational waves. But again, we just don't know. We're just guessing as to the activities. It's xenopsychology. And we can make reasonable, we can sort of lay out all of the possibilities we can think of, but we can't really say that any of them are particularly more likely than any other.
In regards to the Drake equation, over the next, say, 2 decades, are we going to be able to plug in more solid numbers?
Well, we're trying to. I think the next term along will be biosignatures, that we, the FL, the frequency at which life emerges. If we can detect biosignatures in the atmospheres of other planets, or we could detect life here in the solar system, perhaps under the icy crust of Europa and Enceladus, for instance, or on the subsurface of Mars. And we could demonstrate, of course, in the solar system, it would need to be independent life to us. But if we could, I think there's a couple of experiments we can imagine doing, that we have the technology to be able to do, that really could allow us to constrain and perhaps even directly quantify the value of FL. And of course, FI, it's very difficult to say. I mean, as we mentioned, it's possible tomorrow. Right now, as we're talking, someone is detecting a radio transmission. We were just watching Contact last night, and the scene where she detects the radio transmission is so exciting. That could be happening right now, but it may never happen. So for that term, it's difficult. Even if we don't see anything, it's very hard to translate that into any kind of upper limit. Just because we don't detect any radio waves doesn't mean there's no one out there. It just means they're not sending radio waves. So it's really challenging to quantify FI. And that's why in this last paper, I was really using ourselves as a starting point, because at least that's somewhat indisputable that we exist, and we exist in a certain point in Earth's history. But beyond that, it's very, very difficult to say until we have a confirmed detection.
But we are just a sampling of one, ultimately, and one data point. And one has to ask a question. Science doesn't really like absolute uniqueness. You should see other examples. So we should see other examples of civilizations. But the problem is compounded by time. You may not exist at the same time as another civilization in the Milky Way. And if it's in another galaxy, it's even less likely that you would be able to detect it unless they were doing something absolutely crazy, like taking dangerous stars out of the galaxy or something like that. It's the so-called red spiral. So it is actually a lot harder to detect civilizations inherently than one might originally think, as Frank Drake did, looking for giant omnidirectional beacons, which I think that was actually Cocconi and Morrison. But this may be a lot harder than we think it is to detect another civilization. Do you expect it within your lifetime?
I don't expect it. I also don't not expect it. That's kind of cheating a little bit on my answer. I'm kind of on the fence as to. I'd be delighted if it happens. I'd personally, I'm a bit more of an optimist about the nature of contact than I think maybe you are, John, and others. But personally, I very much hope that we can. I mean, just to step back a little bit, There is. I take your point that it's a common observation that anything that has happened on Earth, therefore, must be possible elsewhere. And so, therefore, intelligent life should be possible elsewhere. And that's true. I think anything that can happen, it certainly can happen. It must be possible for it to happen elsewhere. Does that mean it's necessarily likely? Or even within the vastness of 10 to the 22 stars in our observable universe? Not necessarily. If you look at a snowflake, they really are unique. Every single snowflake's unique to each other. And it may be that even though the ingredients, the things which put together a snowflake and put together what makes us intelligent are common, the building blocks are common, that doesn't mean that the precise way in which they're structured is necessarily anything that's likely or probable in the universe. So we may be snowflakes. We don't know. So this is why I try to keep an open mind that it is possible. I know there's a common resistance to that, there's an overwhelming urge to say, no, surely there must be, just look at the number of worlds out there. Surely it must be possible that there's intelligent life out there. And I'd say, yes, it's possible, but we just don't know if it's probable at all. Now, to come back to your point, really, I think, because I was sort of backtracking a little bit there, you're also right there, that this is going to be a long enterprise for us. It could be the thing which defines us as a species. Perhaps it defines all intelligent species, as the act of trying to reach out into the dark and just to contact someone else. We are inherently, we evolved to be a social species. Some of us are quite happy to be hermits and live by ourselves, but most of us reach out and really want to have contact with other humans, other intelligences. And I think as a species, we're kind of the same. We really have this urge and this need to say hello and just to see if there's someone else out there in the dark. And so I think this will be the thing that we do for many, many generations. I hope we can answer it this generation, but I don't think it would stop just after I pass away or anyone else listening to this. I'm sure for generations to come, this will be something that we, I hope, continue to do and appreciate just how important it is.
Now, to dig into the paper, it's a sort of a two-stage question. And the first stage is, how statistically common could life itself be in the Milky Way?
So in the paper, we quantify this term Fi, which is the fraction of life which goes on to evolve into intelligence, Fi. And that's really, as I said, the term that's in Drake's equation. And what's kind of critical is that we don't necessarily we really don't in the paper directly estimate Fi. Instead, we consider two possibilities for Fi. We say either Fi is a very small number or it's a very large number. By large, I mean close to 1. And the reasoning behind that is based off this objective Bayesianism, which I talk about in my video a little bit, and it's obviously in the paper. And maybe a good analogy, and I use this in the video, is to think about chemistry. This was indeed actually the inspiration behind some of the objective Bayesianism work that was done like many decades ago in the 50s. And the idea was, if you were going to dissolve a chemical, you don't know what it is, call it chemical X. It's a new chemical you've just encountered. And you're going to dissolve it into water. And let's say you've got 100 cups of water in front of you. Now, you would expect that either it will dissolve every time, because it's the same experiment. It's literally the same experiment over and over again. It will dissolve every time, F equals 1, or it won't dissolve at all in any of them, F equals 0. It'd be really odd if it dissolved half of the time, like 50-50, or 10% 90 even would be really peculiar. It's like, well, it's the same thing happening over and over again. And so in my paper, because I'm really considering replaying the tape of Earth, it is the same experiment. It's the same conditions, it's the same history of meteorite impacts, everything is the same. And so in that sense, it would be really odd if Fi was at least just focused on the Earth, was some in-between value. And so in the paper, I really consider two possibilities. It's either small, close to 0, or close to 1. And of those two possibilities, it's the rare intelligence which actually wins out. That doesn't mean that Fi is 0, it just means it's a number that's close to 0. But I don't specifically quantify what that number is. That would be a different calculation to make, and a very challenging calculation to make.
Now, in the paper, you also point out that the chemistry of life, the initial chemistry, abiogenesis, had to have been fast, or at least is more likely to have been fast. Can you go into that?
I mean, that's almost an observation that we look at the history of the Earth. We see that the oceans, there's evidence for oceans on the Earth from 4.4 billion years ago. The Earth formed about 4.53 billion years ago. So pretty quickly we had a delivery of water. Either it came from comets, or there's some ideas that it could have even come from the interior of the Earth as well. But however it happened, the Earth had water quite clearly, because we see in the minerals that are produced can only be produced with a body of water. And then within 300 million years of that, you find evidence for carbon-13 depleted mineral deposits, zircon deposits specifically. And of course, life prefers to take carbon-12 over carbon-13 just because it's lighter. It's sort of easier to work with energetically. And so that signature has been identified as a signature of life early on in Earth's history. And that's very fast, 300 million years. Some people don't like that evidence, and they claim that's not conclusive. Maybe there's a process we don't understand that prefers carbon-12 over carbon-13 that's not to do with biology. And so they would defer to later evidence such as direct microfossils. That's really direct evidence for life when you see microfossils. And that would push you back to 900 million years after conditions became habitable. But either way, it's pretty quick within the overall landscape of Earth's 5.3 billion year habitable window. And so those facts, especially the 300 million year one, that's very quick. And we use that timing to make the argument that if you replayed the tape, given there's 5 billion years to play with, the chances are it would happen again. In fact, I can quantify the chances. I would give you almost 10 to 1 odds that it would happen again. I wouldn't give you 100 to 1 odds. I wouldn't give you 1,000 to 1 odds. The reason for that is that there's sort of an anthropic bias effect happening. Again, this is an idea that Brandon Carter talked about a few years ago. And this may be that life had to start quickly, else there wouldn't have been enough time to get to us. And so the fact that life started quickly is suggestive, but it's not a complete slam dunk. That's why I can only give you 9 to 1 odds, because it may be that evolution takes so long to get to us that it kind of has to happen early. Otherwise, we just wouldn't be here to talk about it. And so maybe on most planets, it takes far longer than that, but it's only the ones where it starts quickly, where sentience has time to evolve. And thus we can look back and say, oh, it started quickly. So there's that kind of bias in play, but that's accounted for in the paper. And that's why it pushes the dial back to an optimistic, but still somewhat cautious analysis.
Obviously, that creates a question. According to your analysis, is it likely or unlikely that there is another civilization in this galaxy?
Yeah, I don't think my analysis can directly answer that. There's a couple of reasons why. First is that we really don't know how common truly Earth-like conditions are. And I'm sure many of your viewers and listeners know of this idea of the rare Earth hypothesis. So it may very well be that the conditions on Earth are not necessarily completely unique, but extremely rare. This comes back to ideas such as looking at our sun. Our sun, just recently, it's been shown is unusually quiet compared to most stars. And that's interesting. That may have some impact on our evolution. The Earth-Moon system is unusual in that our moon represents 1% the mass of the Earth. And there's no other moon around any other planet in the solar system like that. If you call Pluto a planet, that would change. But if you don't call Pluto a planet, there's no other moon in the solar system which has such a high mass ratio. And that large moon is important. It stabilizes the obliquity of the Earth. When it was much closer to the Earth than it is today, it would have raised very large tides on that early ocean, tides so large that they would have covered continents. And those continent-covering tides may have been conducive to life, leaving rock pools of water essentially across the landscape, places where life may have had a chance to have got started. And even the plate tectonics may be related to the large moon as well. For instance, the moon impact probably stripped some of the heavy crust, the thick lid of crust that sat on top of the Earth. And once you remove that crust, we were left with a much thinner crust. And that thinner crust is easier to move around and slide about and create plate tectonics. If you make it too thick, it just solidifies, and then you lose plate tectonics. And plate tectonics are, of course, critical for the carbon cycle. So there's a few reasons. You can look at Jupiter. People look at Jupiter a lot and say there's several things about our place that may be unique. So this is why I can't give you a direct answer. I can't take the numbers I've calculated and say that means, therefore, that life is everywhere and that intelligence maybe is unusual, would probably be if I was forced to choose, that's probably what I would choose. Because I just can't say that Earths are truly common. And I can't also say this is the only way to arrive at life and intelligence. There may be other pathways which never occurred here on the Earth. Silicon-based life, is a common example that people speculate about. Maybe even completely different ways of forming intelligence other than the way that we define ourselves as intelligent life. And so I'm really asking the question, how often do you get to something that looks like us? But, there may, so both in a negative way and a positive way, there are other options. But I would take it as at least encouraging. There's good reasons, I think, to think that Earths are common. And so if that's true, then I would expect life to be out there in the galaxy. And that's sort of the direction I'm leaning to recently. And intelligence, I'm just very much open. I would 3-2 odds is not enough for me to place a significant wager. And so I would just keep both options on the table at this point.
Betting odds on the observable universe, all of those galaxies, the billions and billions of galaxies, at some point, is there a tipping point where there has to be other intelligence?
Sure. If Fi was 1 in, let's say it's 1 in 10 to the 11, then that's about the number of stars in the galaxy. And so you would expect that maybe it's just not quite high enough for each galaxy, given that you have to have an Earth-like planet and then it has to have life and then it has to go on to form intelligence. Maybe most galaxies don't have intelligence in them. But if you take a group of 30, 40, 1,000, I don't know, you eventually get enough critical mass that you would expect there to be a success, and intelligence does emerge. Of course, using the framework I've discussed so far, I'm saying nothing about when really that success happens. I'm just saying a success happens over the history. I'm really integrating over the history of the entire planet and saying a success happens at some point in its history. So sure, maybe in a bunch of 100 galaxies, there's a success, and that's us. Or you go a little bit further and we have 2 successes, 3 successes. But those successes could be very disparate in time. There's no, it depends on L, of course, the capital L in the Drake equation. How long do these civilizations last for? That's a very, very critical term, of course, in Drake's equation. And again, one that we don't touch on in this paper, and it's very, very difficult to estimate that term. So that's certainly possible. As I said, we don't really have any idea what Fi is directly. I mean, in my paper, it's certainly possible that when I say Fi is small, it could be 10%. Maybe that's a little bit optimistic, maybe 1%, let's say. Fi of 1% would be pretty much consistent with my analysis. But Fi could also be 0.0000000, keep going, 1%. And that would also be consistent with my analysis. And there isn't really any strong preference in the way I framed the problem between those two. I'm really just asking, is it a small number or a large number? And I think we are interested. I'm having conversations with colleagues right now thinking about experiments we could do to really quantify that, either by looking at the evolutionary record more carefully, looking for artifacts here in the solar system, and trying to think about ways that you can quantify. It's very difficult, but could you quantify the constraints that we see from SETI to say something about Fi?
To extend even further, outside the observable universe, which may be the unknowable, if the universe is infinite outside of what we can see, then other life must exist. And indeed, near copies of ourselves must exist. So do you subscribe to an infinite universe, or do you think there must be limits?
I'm not a cosmologist, and I have to admit, when you pose almost the exact dilemma I have with it. And that's that if the universe truly is infinite, I would go even a little bit further than what you just said and say that if the universe is infinite, there's an exact clone of you, not just like someone who's a civilization that's a little bit like our civilization, but with infinite opportunities, truly infinite opportunities, there would be an infinite number of exact yous having this exact conversation that me and you are having right now out there, which is really, really difficult for me to get my head around. So I sort of hit a a mind block almost when I get to that point. So in a way, it almost doesn't matter though, because when we talk about what's outside of the observable universe, it's almost like here be dragons, because it kind of doesn't matter. It's something which is causally disconnected from us. It is, in essence, a different universe, because there's no way we can interact with it barring faster than light communication or technology, which of course, according to Einstein, should be impossible. So we really do think that the observable universe, at least in astronomy, is all there is worth to talk about. It's interesting to estimate the curvature of the universe and how far beyond the observable universe it might extend. The universe does appear very, very flat, and that's where this evidence, or the possibility, I should say, of an infinite universe comes from. But in a way, it kind of doesn't matter that much, at least for the question of looking for life and intelligence out there in the universe, as long as we accept that faster than light communication is impossible. If we accept that that's impossible, then there's basically no point worrying about what's beyond the cosmic horizon.
And we have to take a break. Today I'm joined by Dr. David Kipping, host of the Cool Worlds YouTube channel. And when we come back, link in the description below, by the way, and when we come back, it's Exomoon time. Now, David, one major area of your research is exomoons.
Yes.
And this is this is an intriguing thing, because I guess we have hints of exomoons, but we haven't really found one. Am I right?
Yeah, we've been, it's kind of a niche field, but a few of us have been looking very hard for exomoons for, let's say, the past almost 10 years now. We know of 4,000, 5,000 exoplanets at current counting, something like that. But we basically have, I'd say, half an exomoon. And that's this candidate that we found about a year and a half ago, I think now, Kepler 1625bi, where the I denotes the moon. It remains a unconfirmed object, though. I'm certainly very excited about this object still. It still remains, to me, the best bet of an exomoon. It's a very strange object, though. So we found this in Kepler data originally. The planet it orbits is a gas giant. It's of similar size to that of Jupiter. It orbits its star at about the same distance that the Earth orbits around the sun. And its sun is of a very similar mass to that of our own sun. But it's a little bit older, it's a bit more evolved, and so it's growing in size. And when we look at this planet, we see evidence for two things. We see that it appears to be wobbling around, and that was actually confirmed with some Hubble Space Telescope data that we got. It wobbles around by about 20 minutes. So it takes about a year to go around its star, but sometimes it comes into transit 20 minutes earlier than it should do, and sometimes 20 minutes later. The Earth-Moon system does the same thing. The Earth wobbles by about 2.5 minutes. This is almost 10 times larger wobble. And the moon, you might guess from that implies a large moon, and you're right. The moon that is implied by that is very large. It's about the same mass as Neptune. And not only do we predict its mass based off that wobble, but we would, of course, expect it to be roughly Neptune-sized. And we see it. We actually see evidence of the moon pass in front of the star just after when the planet passed in front. We can tell the size based off how much light was blocked out, and indeed it's a Neptune-sized object. When we model this system, you see something really encouraging, and that's that the thing which really orbits the sun, this is again true for the Earth-Moon system, is the center of mass between, it's almost like the pivot point of a seesaw, the center of mass between the Earth and the moon is a thing which truly orbits the sun on what we'd call a Keplerian orbit, sort of like clockwork going round and round. And the Earth goes round that little center of mass itself. And so when we look at this system, we notice that if you kind of imagine around this pivot point, the planet is just to the left. It's coming in a little bit later than we would expect it to. It transits 20 minutes later than we would conventionally expect. And so you would expect on the other side, the moon should be coming in early. And so you see that kind of opposite phasing between the two. If one comes in early, the other should come in late, and vice versa. And we see that precise phase shift between the planet's wobble and the moon's relative position as well. So all of these things make it a really nice case for an exomoon. The downside, so maybe that's enough for some people to believe it, but the downside is that this object, we really only have one good data point, and that's from Hubble. Hubble looked at it in May 2 years ago, and we asked actually to get time again. That's what we wanted. I wanted to see this happen a second time, both the dip and the wobble, all of that. If we get a second observation, then for me it would be slam dunk. It'd be like, that's it. There's no doubt anymore that this is real. It's exactly where we expect it to be. It's the same size that we said it would be. Everything lines up. Unfortunately, Hubble time is very, very competitive for astronomers to get telescope time on. It's the best telescope not in the world, but around the world, and it's very challenging to get time. It's oversubscribed by about 20 to 1, and I think that year basically no exoplanet proposals were accepted. All the science was non-exoplanet science, and including us, we didn't get selected. So unfortunately, we didn't get that time, and now it's looking very bleak in terms of the prospect of confirming this thing. You would have to almost reacquire the lock, if you like. Over time, we lose, uncertainty grows over time, just like predicting the weather into the future. The further and further into the future you want to predict the weather, the more uncertain it becomes. And the same way, trying to predict the positions of these two objects becomes more and more uncertain over time. So we can no longer actually make an accurate prediction as to where we would expect the moon and the planet to be. And that was, of course, central to my confidence of a hypothetical confidence of detecting it a second time would be, I expect it to be here. Look, it lands exactly where I expect it to be. Slam dunk. So now we'd have to almost go back to the drawing board on it. So it's a frustrating situation, but it is what it is.
Sounds like we need 20 more Hubble Space Telescopes. Now, back in the day, when I first became interested in astronomy, which would have been something like 1990, we didn't even know that exoplanets existed, but everyone assumed that they did. So it comes back to betting odds. Given that we have a solar system that's literally full of moons, chances are exomoons are ridiculously common in the Milky Way. So it's not really that far of a stretch to expect to find one, right?
Right. I mean, you could say, well, why didn't you use that argument for life in the same way? You see it happen here in the solar system, so therefore you immediately suspect moons are elsewhere out there, and I totally agree. For life, it's a little bit different because that has to happen for us to exist. There's like a causal connection between that event and our existence. But the moons of Jupiter have nothing to do with us, right? I mean, if the Jupiter didn't form its moons, as far as we can tell, that would have absolutely no influence on the evolution and our existence. So it really is an unbiased, fair sample. And in that sense, we have much more confidence using it. It's almost better than, for life, we don't even really have one data point. We have half a data point because of this bias. For the moons, we have not just one data point, but 3 or 4, because, obviously several of these gas giants, all of the gas giants have satellite systems around them. And so it seems very reasonable to expect that moons are common. So I always say it's not a question of if there are moons out there, it's just what do they look like? I think it'd be really strange, and I don't think anybody really contests that, to assume that moons just are only present in our own solar system.
The question, I suppose, the natural extension here is habitability of exomoons. Are exomoons just as good of a prospect for developing life as a proper planet is?
I think there's pros and cons. Some of the cons would be, when you look at most of the moons in our solar system, or all of them really, they're very small, certainly smaller than the Earth. And the Earth is obviously massive enough, has sufficient gravity to hold on to an atmosphere, and that atmosphere appears critical to our success, our evolutionary success. If you took away the atmosphere, maybe you could still have life, but it would be very different. It would probably be limited to subsurface life, almost certainly microbial. It's very difficult to imagine complex multicellular life developing without an atmosphere. If you didn't have an atmosphere, the oceans would boil off as well. So there's lots of major hurdles of not having an atmosphere. And when you make a moon, you take the moon, it's 1% the mass of the Earth, 1.25%, but it's about a quarter of the size. It's about 25% the size of the Earth. That's not too bad, right? Not too shabby. It's a quarter of the size of the Earth, and yet despite that, it clearly doesn't have sufficient mass to hold on to an atmosphere. It has 1/6 the surface gravity of the Earth, and that's evidently not enough to hold on to an atmosphere when you're orbiting the sun at the distance that we orbit the sun. Now, if you take Titan, people often point at Titan and say, hold on, Titan's about the same size as the moon, and that has an atmosphere. But that's a different story because Titan's much colder. Titan's really distant from the sun. And so because of that, the molecules in the atmosphere are moving far slower. They have much less energy. And so you need less gravity to hold on to that atmosphere. If you want to hold on to a warm atmosphere, like the Earth's atmosphere, then you're going to have to be more massive. So there's some argument and debate about where this threshold really happens, but it's clearly heavier than 1% the mass of the Earth. Even Mars kind of struggles to hold on to an atmosphere, has a very tenuous atmosphere at 10% the mass of the Earth. So a lot of us sort of point it around sort of a third of an Earth mass as maybe being the threshold. And we don't have any moons that large in the solar system. So this is maybe the downside. If moons never get that big, if they never get to be a third of an Earth mass, then we really shouldn't expect there to be any habitable moons out there, at least not habitable in the sense of the Earth's habitability. I sometimes like to delineate and say there's cryohabitable. Cryohabitable is a term I sometimes use to define like Enceladus and Europa, where you could have subsurface water and oceans and life. And there's sort of telluric habitable, which is a planet which truly represents something more like akin to the Earth. And I think, obviously the cryohabitable worlds are interesting in their own right, but many of us are probably most excited about the prospect of detecting truly Earth-like conditions on another world. So this is up in the air. And if Kepler 1625bi is real, that would kind of solve it, because it would show, hey, there's no problem forming a third Earth mass moons. In fact, you can get all the way up to 20 Earth mass moons and still have no problem making them. So that's why it's a very important object, and confirming it would have implications about habitability. And that's the downside, but there's also many positives. So on the positive side, a moon maybe doesn't necessarily have to be massive enough, has to be massive enough probably to hold onto an atmosphere, but it might not have to be massive enough to hold on to a magnetosphere, to have an internal dynamo, because it could probably hide inside the magnetic shield of its home planet that it orbits. This is work that astrobiologists such as René Heller have been demonstrating lately. So the moon may not even have to have a sufficient magnetic field. It could have a very weak magnetic field, but still get sufficient protection and shielding thanks to its home planet. And then another interesting example of the benefits of being a moon would be tidally locked planets around M dwarfs. So of course, if you're in the habitable zone of an M dwarf, because the star is so much less luminous, the habitable zone is much closer, and that causes the planets, we think, to tidally lock to the stars. And that could lead to atmospheric collapse. You have one hot side, one cold side. That could be bad for the planet. But the moon would be fine. If there was a moon around that planet, it would receive equal amounts of illumination on both sides. This is why I like to say there's no such thing as the dark side of a moon, but there is such a thing of a dark side of a planet. These tidally locked planets really do represent that. But even if the moon is tidally locked to the planet, it will still get equal amounts of illumination. The far side of the moon gets equal amounts of illumination to the near side. That's a fallacy that maybe Pink Floyd helped propagate with their album. So there's many benefits of being a moon as well.
Pink Floyd, Roger Waters destroyed astronomy by calling it the dark side of the moon. David, I think an obvious thing here is that we don't just have Europa and Enceladus. We have a lot of moons in this solar system that have some layer of liquid water, or hypothesized layer of liquid water, which opens up a completely new avenue for life, because it is liquid water, or a water and ammonia mix. So that may be a more common venue for life than an Earth-like planet. But it seems to me that it would be limiting. How complex do you expect that life could get in a place like a European ocean?
Yeah, I think that's a hard question for me to answer as an astronomer. I think a biologist or an evolutionary biologist would probably be able to give you a much better answer to that than myself. So if my guess would be that it would be somewhat limiting. Just the energy supply is clearly going to be less from an energetics perspective, and energy is clearly necessary to develop complexity. If you're really clinging on to existence, around these sort of black smokers that we have at the bottom of the Atlantic Ocean, for instance, you have something like this as your energy source, you look at the life around it, and it's difficult to imagine that becoming extremely advanced life, at least sort of the life that might be capable of building a radio transmitter, for instance, if you're limited to just sort of clinging around these black smokers. So it's certainly very important and interesting to try and look for life in those worlds. There's also a challenge of how do you do that? I mean, we're interested in visiting many of these icy moons, as you say, but Enceladus and Europa tend to be the two favorites that people talk about as a possible mission one day, just because it's presumably more accessible. Because it's covered in ice, it has an ice crust, it should be easier just to drill through that or melt through it to get into the ocean. But then you have the problem of contamination. Accidentally bring along a hitchhiker bacteria from the Earth, tardigrade or something that could cling onto the side of the rocket, and now you've injected another life form into that biosphere, if you like. And especially for those icy moons, they probably are somewhat pristine compared to Mars, let's say. So Mars has frequent material swapping between the Earth and Mars through meteorites constantly being knocked off and exchanging between them. So there's a good chance of panspermia between Mars and the Earth, especially in the past when Mars was warmer and had liquid water on its surface. And most recently, we've been seeing this for Venus as well. There's evidence that Venus was habitable for a long time as well now, maybe 3 billion years. So for both of those, there's probably a good chance of interchange. But Europa and Enceladus are not only much further out, they're in the outer solar system, and it's hard for material to go that direction because you're going against the currents of the sun's gravity, if you like, to leave in that direction. It's harder. And then even if you are a meteorite that makes it to Europa, you have like several kilometers of ice to get through before you can get into the ocean and contaminate the life there. So this is why people are very interested in like the Vostok ice lakes, in these Antarctic ice lakes as pristine tombs of ancient life that may have been present on the Earth. And in the same way, I think there's a big challenge with how do you go around exploring, confirming life on these subsurface life, Europa and Enceladus, without accidentally bringing in the thing that you're looking for. And Earth life might outcompete the life that's there, which of course would be disastrous. You're basically killing the thing that you're interested in. So this is very challenging. I'm not sure how we're going to solve that problem.
Well, prudence, I suppose, would dictate that we solve the problem before we even go there to make sure that we actually independently confirm another genesis of life on Europa without, muddying the waters. But at the same time, if we did that and we found that Europa has life and it's genetically related to us, then that brings panspermia to a completely different level, because then it isn't really alien life. It's either we are from originally Europa, or Mars, a rock got blasted off of Mars and landed here and seeded life, or vice versa. And I think, to me, that's going to be the most interesting question in the next coming centuries to answer, is that if we did find life on these worlds, is it related or isn't it? And if it is related, where did we originate? Did life start on Mars and come here through panspermia, or vice versa? And because Earth was really not that great of a planet for life when life seems to have arisen. So you're left with this question of, was there a better place? And at the time, Mars sort of looks attractive, so we may end up being Martians. Do you
or even Venusians,
as
well, as I said, that's also on the card. And
there are questions about Venus's upper atmosphere, if it still might be habitable, and that anything that microbes or whatever that might have came into being on the surface of it when it had water might still be in that upper atmosphere and have evolved to deal with the conditions of it. And I think people forget that a lot, that Venus is actually a very attractive candidate for microbial life. And it's actually an attractive candidate for human colonization if you're in the upper atmosphere, because that's basically the most Earth-like conditions in the solar system is in Venus's upper atmosphere. So I think it gets ignored. Venus gets ignored too much. But ultimately, though, that sort of points towards there are a lot of possibilities for habitability, at least microbial, in this solar system alone. And then the rest of the galaxy has to present the same conditions, right?
Yeah, we would think so. That's certainly the conclusion of my recent paper, and I think astrobiologists tend to be optimists in that same sense. And there's the consensus wanes with the fashions of the time, but I think certainly there's a lot of optimism that the processes which formed life, even from a chemical perspective, looking at the early, the Miller-Urey type experiments, seems that making complex organic molecules isn't that hard. And these things are abundant. Even in comets, you can find them. For instance, in interstellar dust, you can find urea. So there's like complex organic molecules everywhere. So I think there is an optimism that that life may be common. When we look at when we're looking for these signatures of life elsewhere outside of the solar system, it's a very different game, though. In a way, these icy moons, as fascinating as they may be, it's going to be very difficult to imagine how we would possibly confirm evidence for life in an icy exomoon, because the signatures of life are all hidden from view underneath this lid that's hiding the interesting stuff away from us. When we think about more like Earth-like worlds, Earth-like moons or planets, at least then the atmosphere is accessible. And if life is on the surface, it should be presenting itself indirectly into the atmosphere, and we can detect those signs as well. So in terms of the prospects of detecting life in our lifetimes, I think Earth-like planets are almost certainly going to be the big focus for us, just because we have a sense that we could do it. But we're certainly not discounting those icy moons. But my best bet would be if those have life on them, we're almost certainly going to find that in the solar system before we start having any chance of seeing it for exomoons.
All right, David, we are out of time. Thanks for joining us again, and I look forward to our next chat.
Yeah, my pleasure. Thanks for having me.
John, Beatrice Villarreal sent us an email about a project she's working on, and I volunteered you to help.
Beatrice, you say? She was a great guest. I'm intrigued.
You're always talking about citizen science, so Beatrice has asked us to help her out.
Well, that sounds interesting. I love citizen science. The vanishing and appearing sources during a century of observations, VASCO, is a project that uses images of the sky from the 1950s and compares it to images of the sky today. I like the sound of that.
I thought you might.
So maybe our viewers could help too.
The link's already on screen.